Question 14. A battery of negligible internal resistance, this one, is connected to a resistor network. An ammeter and a switch S are shown. When S is open, the reading of this ammeter is 250 milliamps. When S is closed, what is the change in the reading of the ammeter? This is a circuit, the same circuit when the switch is closed. So we have this resistor, 7.2 and 2.8. So is provided the current that is flowing when the switch is open, but we cannot go that far without knowing the voltage here. To solve this problem, we are going to find the value of voltage based on the prior information when the switch is open. So when the switch is open, so we have the same resistor here, and this one doesn't count because there is no current flowing here. With these two resistors in series, we can calculate the voltage across these 4.8 ohms resistor and 7.2 ohms resistor by using Ohm's law formula. Doing the substitution here, we have 4.8 ohms times the current is 250 milliamps, so milli is 10 to the minus 3. Likewise, on this side, we have 7.2 ohms times the current, which is 250 times 10 to the minus 3, because this is milli. This resistor is not included in our calculation here, because since this switch is open, there is no current flowing on this resistor. For a circuit in series, so the total voltage is equal to the voltage drop on one resistor, in this case 4.8 ohms, plus the voltage drop on this resistor, 7.2 ohms. So the value of this voltage here is 1.2 plus 1.8, which is 3 volts. So that is the value of our voltage. So now we are going to use these 3 volts for our situation right here. Back to the circuit. Now the voltage is the same. The voltage of a battery is the same regardless what's going on in this circuit. So that's why we are using the same value. One note here, the voltage is the same. However, when we add a resistance to a circuit, the current changes. And this is the question for this problem. What is the change in current when you add the circuit? We have originally 250 milliamps with this switch open. Now that is closed, so how much you affect the ammeter? Let me compare before and after. So before, when the switch is open, the total current flowing in the circuit was 250 milliamps. That was read by this ammeter connected in series. So we use the circuit to calculate the voltage supplied by this battery. So the voltage is the same. Now the current will not be the same. Now you have a total current here that we need to calculate, because this current is going to split right here between those two resistors. So we need to find, we have the total voltage, which is 3. Now we need to find the total resistance. So back to the circuit. So we have the total voltage, yes, we do, 3 volts, but we need to calculate the total resistance. Here is a quick way to solve this. So we have a 4.8 plus in series this resistor is in series with these two in parallel. First, I'm going to solve this. 7.2 in parallel with 2.8. 7.2 inverse plus 2.8 inverse equal inverse one more time. So that is my total resistance here, partially plus this one plus 4.8. So that is the value of my total resistance. Back to this, to calculate the total current for this new scenario, 3 volts divided by this total resistance. So I'm keeping here all the decimals in my calculator. So what I'm gonna do is I'm going to, because this is on the denominator, you don't have to do how I'm doing here, inverse times 3, and that's the value of my current for this scenario, 0.440 amps. Because all the options for the answers are in milliamps, so it will be a good idea to convert these in milliamp as well. So these will be 440. Milli is 3, so 10 to the minus 3. Okay, so I move the decimal places, 1, 2, 3. So 440 times 10 to the minus 3. This is 440 milliamps. So now we can find the change in the reading of the ammeter will be 440 milliamps minus 250 milliamps. So the difference is 190 milliamps, option C. This question definitely requires some of your skills to determine that missing factor, like for example the voltage, how to find the voltage with 2 resistors in series, because you need to know this, that in series the voltage supply is equal to the voltage drop, the sum of the voltage drop on each resistor in the series circuit, and then we could determine that the value of the voltage is 3, and then we replace this value here when this resistor is now added to the circuit, and now we need to find the total resistor, and this is in parallel plus series, and then you need to find the new total resistance for this scenario, and this is the difference between them. Moving forward with question 15. 2 copper wires are joined together and carry a current. So the current here is the same. Wire P has a diameter D and wire Q has a diameter 2D. What is the ratio between the average drift speed of the free electrons in the wire P and in the wire Q? So let's understand the formula variables. I is equal NAVE, navy. They are all related to a wire. So I is the current that is flowing in this wire. N is the number density, which means is the number of electrons per volume. Just like regular density that we know, that is mass over volume. So in this case, it will be the number of electrons per volume. So that's called number density. A is the wire cross-sectional area. So remember that the shape of a wire is a cylindrical shape. So the area, cross-sectional area, will be always circular, and the volume will be like a cylinder type of volume. You need to find the volume of a cylinder. Volume of a cylinder, just a side note here, is the length times area. So that's very simple to, we have the length, you have the area, so you can calculate the volume of a cylinder. V is the drift velocity, is the speed of the electron in the wire. And E is the charge carrier. So sometimes the problem refers to the charge carrier is the electrons, which is the most common. And the charge for electron is 1.6 times 10 to the minus 19 coulomb. Sometimes they will say the charge carrier is a proton. So the proton, the charge, elementary charge for the proton is the same, 1.6 times 10 to the minus 19 coulombs. So those are the variables that we need to understand and identify each one. So back to our problem. It's asking to find the average drift speed of a free electron. So it's talking about the V for the wire P for this section and the V for the wire, the section of the wire that is called Q. So first step is rearrange the formula in terms of the drift velocity. So the drift velocity in this case will be the current over the number density times the area, sectional area, times the charge of the electron. Okay, so now we have the drift velocity of the wire P over the drift velocity of the wire Q. The problem states the current flowing through both wires is the same. So then we can cancel this. Also, the charge of the charge carrier, in this case the electrons, are also the same. Then we can cancel this. Now, N, which is the number density, is more related to the type of material. So we have a specific number density for copper, for silver, for gold, and different types of metal. Now here the problem states that those two wires, they are copper wire. So they have the same material, the same N. For this reason, we can cancel N as well. So what is left from this? So we have here on 1 over A P, and the other one is 1 over A Q. So the sub just to identify the area of the section of the wire. To solve this, I keep the numerator and I flip this fraction on the denominator. So it will be A Q. After all the substitution, so you can cancel pi over 4 on both. And what is left is on the numerator now we have 2d squared will be 4d squared. And on the denominator we have d squared. So now we can cancel this. And finally, the ratio between both drift velocity is 4. And this is our option D. So the overall idea about this problem is to understand the formula for current related to drift velocity and cross-sectional area of a wire and the number density. And once you understand all those terms, so you can derive a formula for drift velocity and find the ratio between the drift velocity of the section wire P over the section wire Q. I all the time have problems to say Q. And then you will just eliminate all those terms that are equal. I mentioned that the current flow is the same. I mentioned that the material is the same, is copper, which means that the number density is the same value, and is asking for the free electrons, so it's talking about the same charge. So that made way easier to solve this problem. Question 16. A network consists of 3 ohm resistor and 2 6 ohms resistor as shown in this picture. The potential difference, or PD, across this network is 4 volts. What is the current through the 3 ohms resistor? Before moving forward, I want to make a note here. This is a PD, not an EMF. EMF usually represented by a battery because EMF converts chemical energy from the battery to electrical energy. And PD uses this electrical energy to make other forms of energy. So in this case, we just have resistors here, and pretty much it's gonna just get a little bit warm. That's the only indication of the conversion of the electrical energy into heat energy. This circuit can be redesigned with, like this one here. We have 3 in parallel with 6. And then now both are in series. So now we can find the current flowing in this resistor, on both resistors, because they are in series. And when we have the current on each, across each resistor, we can find the voltage across this guy, and we can find the voltage across this one. But first we need to find the equivalent. So the equivalent between 3 and 6 is 3 inverse plus 6 inverse equal inverse one more time, and that's 2. I cannot move forward because I don't know the value of current. So let me slide right here on this space. So now we need to find I. So the voltage is 4, and the sum of those resistors is 6 plus 2, which is 8. So our current here is 0.5 amps. Now with this information, let's go back to where we stop. So now we have V is 6 times 0.5, so V is 3 volts, and V here is 2 times 0.5, and V here is 1 volt. Voila! Makes so much sense. So the voltage here on this guy is 3 volts, and the voltage on this branch, they are in parallel. They have the same voltage here because they're in parallel, is, let me put right here some spot, 1 volt. And the PD in the circuit is 4, so makes sense. 3 plus 1 is 4. So to answer the question, what is the current through the 3 ohm resistor right here? What is the current right here? This is not the one. This current is the current that actually flowing up to here, right? So this is I. So this is our the current on this. And why I'm saying this, because when this current hits this joint, it's going to split. So it's going to split between this and the current flowing on 6 ohms. So now we need to calculate this, the current on this resistor. So we are going to use the same ohms formula. Current on this resistor is the voltage on this resistor, which is 1 volt. Calculate here, divided by the value of the resistor, which is 3 ohms. So that gives us 0.33 amps. So this is the answer. Question 17. A power supply of electromotive force, EMF, V, and negligible internal resistance is connected in the circuit shown here. There is a current of 3 amps in the 4 ohm resistor. What is the value of V? Okay, so V is the voltage that is going to be shared between these 3 ohm resistor and these 2 in parallel. So we have the voltage here and the voltage here. So V is going to be equal to V1 plus V2. We can calculate the voltage on across this 4 ohm resistor because we have the current. So in this case, the voltage on 4 ohms is the resistance, which is 4 ohms, times the current, which is 3 amps. So the voltage on this guy is 12 volts. Because those two resistors, they are in parallel, so the voltage here across 4 is the same across 2. So the voltage on 2 ohms is equal to 12 volts as well. Okay, so what will be the current flowing through this resistor? So the current flowing on this resistor will be the voltage across this resistor, which is 12 volts, over the value of the resistor, which is 2 ohms. And this is the current flowing here is 6 amps. Okay, so where I'm getting with this? So the problem is asking to find the value of V. I already found one. My V2 is 12, but I don't know V1. So if I find the current flowing here on this resistor, so I can find the voltage on this guy, and then I can calculate my final value of voltage here, the EMF. So let's blend here with Kirchhoff's first law. Kirchhoff's first law says that the sum of the current entering in a joint is equal to the sum of the currents leaving the joint. So here we have just one current, that is the current that is flowing through this resistor right here, 3, and we have the 3 amp plus 6 amp. So the current on this resistor is 9 amps. Finally, I call this V1, it's fine. V1 is RI. So this R is for 3 ohms and I is the current flowing on this resistor. It's good to label everything so we don't cross values on a circuit like this. Okay, so my R is 3 ohms and the current is 9. So the voltage on this, across this resistor, is 27 volts. Finally, my EMF right here will be my V1, the voltage on this, plus the voltage on these two in parallel, which is 12. So my V1 is 27 plus 12 volts. So the answer is 39 volts. Okay, so let me review with you the sequence that I did to find the answer. So step 1, I calculate the value of the voltage on this resistor because the current was provided. Since those two are in parallel, so the voltage across here is the same here. So that was my step 2. By my knowledge of the two resistors in parallel have the same voltage, so the voltage on this resistor is the same. So using that information, I calculate the current flowing on this resistor 2. Now I move to step 4. In step 4, I use Kirchhoff's first law and I calculate the current flowing in this resistor. And then I use this information and I calculate the voltage across this resistor, which is 27. Finally, I add this voltage with this one because that is, we can easily figure out the voltage here is V1 plus V2, so 39.